Yeah, so I hope you still give me a clap after my lecture. So, so it's a great honor for me to give this lecture. So this is the title of my lecture, Euclidean Traveler's Journey in Hyperbolic Worlds. And this is the pictorial title of my lecture. So my goal is to try to explain what this picture means. Okay? So in other words, so we'll discuss possible closures of a Euclidean line in various geometric spaces. So we'll imagine a Euclidean traveler. So she's our Euclidean traveler. And by Euclidean traveler, I mean that she's going to travel along Euclidean line, visiting many different geometric worlds. Okay? And our question will be, what places does she get to visit, does she get to see in each of these geometric worlds? And here is her itinerary. So in 1884, she's going to travel to Euclidean torus, guided by German mathematician Kronecker. And then about 50 years later, she's going to travel to close the hyperbolic surface, guided by Hedlund. And then in about 55 years later, she's going to travel to close the hyperbolic manifold of a higher dimension, guided by Ratner. And then she's going to adventure to hyperbolic manifolds of infinite volume. Okay, so before she starts her serious journey, so she's going to need some exercise, and then she's going to jumping on the circle. Okay, so the circle, in a complex plane, so this is a complex numbers of modulus 1. But we can also represent the circle in an additive model, R by Z. Okay? So the correspondence is given by this. So of course, every complex number of modulus 1 can be written as e to the 2 pi I x for some real number x. And then the map, which maps e to the 2 pi I x to x, this gives the bijection between this multiplicative model and then this additive model. So we'll think of the circle in two ways. And I'm going to denote by r sub theta. This will be a rotation by the angle 2 pi theta. So here's the picture. So I have this circle, and then r theta is a rotation by 2 pi theta. And in the multiplicative model, this is just multiplication by e to the 2 pi I theta. And in the additive model, so this is simply adding theta. Okay? So x goes to x plus theta, but of course modulo z. So, and we'll be iterating these rotations. So you can imagine, so she's standing here, and then she's going to start to jump, okay, by the angle 2 pi theta. Or in the additive model, she's going to jump by the distance theta. So the orbit of a point x under the iterations of r theta, in the additive model, this is simply x plus all the integral multiples of theta, okay, x plus n theta. Or n in integers. So it's clear, I mean, if the theta is rational, okay, so you go by 2 pi theta, and so on. And then if it's a rational number, you will come back to the same point. Okay? So in that case, the orbit of r theta will be closed, finite, periodic. And if theta is irrational, then the orbit will be dense. You never come back to the same place. Okay? So you can interpret this result. If she's jumping by the rational distance, then she will see only finitely many places on the circle. And if she's jumping by irrational distances, then she's going to see all the places in the circle. Okay? Now we move to the 2 torus. So 2 torus is just the product of 2 circles. Or in the additive model, this is R2 by integral lattice Z2. So consider this projection map R2 going to R2 by Z2. So this is simply the canonical quotient map. So I need to know what is a Euclidean line, right, to define what this Euclidean traveler means. And in R2, in the plane model, we know what a line is. We have this line, and then by a line or Euclidean line in the torus, we simply mean the projection of a Euclidean line in R2 to T2. Okay? So, for any point omega 1, omega 2, so I'm going to denote this L sub omega 1, omega 2 to be the projection of the line connecting the origin and this point. Okay? So I have this line in R2, and then L sub omega 1, omega 2 is going to be the projection of this line under the quotient map, R2 going to R2 over Z2. Okay? So now imagine, so my traveler travels along this Euclidean line, L omega 1, omega 2, and then which places will she be able to see? Okay? So it is useful to actually think of this unit square, which is the fundamental domain for R2 over Z2. Okay? So this means that, so I have here these 2 vertical lines labeled by A And the transformation, so which I denoted by tau sub A, is just adding 1, 0. So this 1, 0 identifies the two vertical lines. And then this is called the side pairing transformation. And these two horizontal lines labeled by B, they are identified by tau sub B, which is just a translation by 0, 1. Okay? So we identified vertically and horizontally, and then we obtain this torus R2 over Z2. Okay, so now, so imagine, so she travels along this line in R2, and then when she reaches the boundary of this fundamental domain, which will be the point 1, the slope of the line, right? 1, omega 2 over omega 1, she gets instantly moved back to the y-axis, which will be the 0, omega 2 over omega 1 by the side pairing transformation. And then she has to travel along the line with the same slope. Okay? And then you travel like this. And then when she reaches the boundary, again, she gets moved to the y-axis and so on and so on. Okay? And then now if you see actually which places she's visiting on the y-axis, this is exactly the integral multiples of the slope, omega 2 over omega 1. Okay? So then by the previous theorem, she knows from the exercise, if the slope is a rational number, then she's going to visit only finitely many places in this y-axis. And that would mean, in terms of the torus, so here her journey becomes periodic. Okay? So it becomes periodic. And if the slope is irrational, then she visits all the places in the y-axis. That would mean that she's going to visit all the places in these two torus. So this is indeed Kronecker's theorem in 1884. Any line in the two torus is either closed if the slope is a rational number or dense, it's everywhere. So now we move to the higher dimensional torus. So higher dimensional torus, by that I just mean, okay, Rn divided by the integral lattice Zn. And then again, we have this quotient map. And again, the Euclidean line in this higher dimensional torus is simply the projection of the line in Rn to Tn. So in dimension 2 case, we had this dichotomy. So every Euclidean line in two torus is either closed or dense. But in higher dimension case, we don't have this dichotomy anymore because the higher dimensional torus can contain a torus, subtorus of a smaller dimension, which is the projection of some rational subspace of Rn to the torus. Okay? But nevertheless, actually, that is the only possibility. So the Kronecker theorem, again, 1884, applies to any dimensional torus here. And it says the close of a line is always a subtorus. And we also know the dimension. So it's a k-dimensional subtorus of Tn, where k is the dimension of Q vector space spanned by this omega 1 to omega n, which determines the line. So here is a slight more generalization. So instead of considering Zn, we can actually consider any co-compact discrete subgroup of Rn. So by co-compact, I mean the quotient is compact. Okay? And it's not hard to prove that any co-compact discrete subgroup of Rn is of the form. It is a Z-span of some basis of Rn. So gamma always looks like this sum of ZVI, when V1 to Vn is a linear independent vectors in Rn. Okay? So in this generality, the statement is the following. So for any Euclidean line L in Rn over gamma, so this is again a torus. The close of the line is a subtorus, meaning that there exists some linear space V in Rn, such that the close of the Euclidean line is this linear space divided by a lattice inside this subspace. So in fact, actually, so we don't have to insist that this Euclidean line passes through origin. So we can also consider line which does not pass through the origin, right? It could be a fine line. In that case, we have to allow the translations in our answer. Okay, so if you allow the Euclidean line, which are not necessarily passing through the origin, then in the answer, we have to add this up to translations. Okay, so now she wants to travel to close the hyperbolic surface. And close the hyperbolic surface will be a quotient of hyperbolic plane. So now I want to define what the hyperbolic plane is. So in a fancy term, hyperbolic plane is a unique, simply connected two-dimensional Riemannian manifold of sectional curvature -1. But you can forget about this definition, because I'm going to give you actually very simple and very nice model of a pop plane. Okay? So a pop plane model is simply, so we have this R2 and then you divide the R2 by x-axis, and then it's just above the open half plane. Okay? So H2 is going to be simply the set of all x comma y with positive y. It's an open space. Okay? So here's the picture. It's just open, and then this line here is the boundary. It does not belong to H2. And the hyperbolic metric is given by the Euclidean metric divided by the second coordinate, the y coordinate. Okay? So what do I mean by this symbol? So this means that for 2 points, P and Q in H2, the distance between P and Q is computed in this following way. So you consider all the possible, say, differentiable curves connecting P and Q. I have 2 points, and then consider all possible differentiable curve connecting P and Q. And then you look at the integral of this expression, and this expression is given by this formula. Okay? So it's the Euclidean norm of this derivative of t divided by the second coordinate of the curve. Okay? And then you look for the infimum of this quantity. So note that if I have 2 points, P and Q, which are very close to the x-axis, okay, that means that the y-coordinate is very small. That means the hyperbolic distance between 2 points close to the x-axis is much larger than the Euclidean distance because you divide by something very small. Okay? And then conversely, if you have 2 points, P and Q, which are very, very high above, then their distance is much smaller than the Euclidean distance because I'm dividing distance by the height. And in this model, the hyperbolic lines or geodesics, so by this I mean that it's a distance minimizing curve. Okay? The distance minimizing curve are called geodesics. And geodesics between P and Q are of the following form. So if my P and Q is in this position, then the geodesic connecting P and Q lies in this vertical line, or they are actually the semicircles meeting the boundary orthogonally. Okay? So that means that if I want to travel from P and Q, from P to Q in the fastest possible way, then we must follow these trajectories. Okay? These are hyperbolic lines, but they are not Euclidean lines. So another very convenient model is the unit disk model. So in the unit disk model, this is simply an open disk of radius 1, and then the hyperbolic metric in this model is the, again, Euclidean metric divided by this quantity, which becomes very, very large when you approach the boundary of the unit disk. Okay? And then geodesics in this model, these are again lines or circles, but intersecting the boundary orthogonally. So these are geodesics in this disk model. So now, what is a closed hyperbolic surface? So by a closed hyperbolic surface, I mean it's a compact hyperbolic surface, but without boundary. So that's what I mean by closed hyperbolic surface here. So how does a closed hyperbolic surface look like? And of course, H2, this is not compact. It's not closed hyperbolic surface. So remember what was Euclidean torus? So Euclidean torus is the quotient of R2 divided by discrete co-compact subgroup of R2, right? That was the Euclidean torus. So in analogy, we would like to say that a closed hyperbolic surface is a quotient of H2 by gamma, where gamma is a discrete co-compact subgroup of H2. Okay, so that's what we wish to say. But the problem with this statement is that this H2 is not a group. So it doesn't make sense to say gamma is a subgroup of H2. On the other hand, we'll see very soon, H2 is not a group, but it is almost a group. It is very, very similar to its isometry group, and then this sentence actually will make a sense. Okay? So what is the isometry group of H2? It is this group, which is very familiar to us. So it is, in fact, PSL2R. So this PSL2R is the group of 2 by 2 matrices with the real coefficient of determinant 1, modulo plus minus 1. Okay? So to explain why PSL2R is isometry group of H2, so I'm going to now view H2 as a subset of the complex plane. Yeah? So we can identify R2 with the complex plane C. So then H2 is simply x plus IY with this imaginary part Y positive. Okay? And the action of PSL2R on this H2 is given by this linear fractional transformation. Okay? So we map, so if A, B, C, D is an element of PSL2R, then it's going to map Z to AZ plus B over CZ plus D. Okay? So using the fact that actually, so this is a determinant 1 and the real matrix, one can check that if Z has a positive imaginary part, then this resulting complex number will also have a positive imaginary part. So PSL2R indeed preserves H2. Okay? Moreover, you can check that PSL2R preserves the hyperbolic metric we described. So which means that every element of PSL2R gives us an isometry of H2. So by isometry, we mean it's a transformation which preserves the distance. Okay? So moreover, it turns out PSL2R is exactly the group of all orientation the group of all orientation preserving isometries of H2. Okay, so we have this identification. So PSL2R moves some point in H2 to another point by isometric action. And moreover, this action turns out to be transitive, so which means that any 2 points in H2 can be moved from one to another by an element of PSL2R. So now if you look at the map, G goes to, so now think about this map I. It's a pure imaginary number. And then if I apply PSL2R to I, then I see all the points in H2. And it's easy to compute the stabilizer of this point I in this section. This is exactly the rotation group, SO2. Okay? So this gives us identification of H2 with this quotient of PSL2R divided by this rotation group, SO2. So this is what I meant by H2 is almost a group, because SO2, this is a compact group, it's a rotation group, it's not very large. So H2 is almost PSL2R. Okay? This viewpoint is quite important. So indeed now I can say exactly what a closed hyperbolic surface is. Closed hyperbolic surface now is a quotient of H2 by gamma, where gamma is a discrete co-compact subgroup of H2. And more precisely, of isometry group of H2, which is PSL2R. Okay? So this is our definition of closed hyperbolic surface here. Okay? So by this quotient, we mean actually all the points lying on the same gamma orbit, they are just 1 point. This is what the quotient means. Okay? So of course, you can ask, well, I gave a definition, but does it exist? Does there exist a closed hyperbolic surface? So here is one example, one very explicit example. So I'm using now here this Poincare disk model. Okay? So this is a hyperbolic plane, but in the disk model. And then consider this regular octagon. Okay? So here, each side is a part of a geodesic. Remember the geodesic in the unit disk model, these are the circles which intersect the boundary orthogonally. So here the sides are hyperbolic geodesics. So I have a regular octagon, and then the angle, the inner angle is pi over 4. Okay? And I have here 4 labels, A, B, C, D. Okay? And we identify 2 sides with the same label, and then we get actually then this, this donut with the 2 holes. Okay? So if I look at these 2 sides labeled by A, then there is an isometry which moves this side to this side, which we call side pairing transformation. So if I denote that element by gamma sub A, and then similarly for other pairs of sides, we have gamma sub B and gamma sub C, gamma sub D. These are elements of the isometry group of H2, and they generate a subgroup gamma, okay, which is a subgroup PSL2R, and then the quotient surface H2 by gamma. So this is this hyperbolic surface with 2 holes. So this is a closed hyperbolic surface. This is compact surface without boundary, and then it has hyperbolic structure. So topologically, any closed hyperbolic surface is always a donut with at least 2 holes. And conversely, in fact, actually, any donut more than 2 holes actually can be realized as a closed hyperbolic surface. And moreover, if you look at actually space of all closed hyperbolic surfaces, which is topologically donut with G number of holes, then this space up to isometry, this can be parameterized by R to the 6G minus 6. Okay? So this space is called the Teichmüller space, and then it has this huge dimension. So the point I want to make is that there are many, many closed hyperbolic surfaces you can travel, okay? And it is a huge space, it's uncountable, and its even dimension is 6G minus 6. Okay, so now for her to be able to travel, she has no what is a Euclidean line, because she's allowed to travel only along a Euclidean line. Okay? So in H2 here, so Euclidean line will be simply this horizontal line over height 1. Okay? So this looks like a Euclidean line, right? So we are going to call this is a Euclidean line. But in the geometric space, the objects which are isometric to each other, they should be given the same name. Okay? So then we'll call all the isometric image of this line also a Euclidean line. Okay? So if you apply element of PSL2R to this horizontal line, what you get is either another horizontal line or this circle, which is tangent to the boundary. Okay? So all of these objects will be called Euclidean lines. And another name for Euclidean line in hyperbolic plane is a horocycle. Okay? This horocycle is kind of imaginary circle because you see actually this circle is not a circle in H2 because this tangent point, it does not belong to H2. Okay? H2 was the open half plane, so it is not exactly, this is not a circle in H2. It is an imaginary circle, so it's called a horocycle. Okay? So this is a Euclidean line in H2. And as before, by a Euclidean line in closed hyperbolic surface, we simply mean the projection of a Euclidean line in H2 under this quotient map. So we have the canonical quotient map going from H2 to H2 mod gamma, which is my closed hyperbolic surface. And then here I know what a Euclidean line is. And then by a Euclidean line in these surfaces, I simply mean the projection. Okay? So yeah, so I know, now she knows what the Euclidean line here is, and then so she wants to travel along this Euclidean line. So the question is, where does this Euclidean line, Euclidean traveler get to visit in this hyperbolic surface? Okay? So as in the torus case, it is useful to look at this fundamental domain picture. Okay? So here is the regular octagon. So you have to believe me, this is regular because you see this hyperbolic distance is same as this hyperbolic distance. Okay? Because as we said, when you go down to x-axis, the hyperbolic distance between these 2 points is much larger than Euclidean distance. Okay? So she travels along this Euclidean line, and then when she reaches the boundary of the fundamental domain here, she gets instantly moved to another side of the fundamental domain by certain side pairing transformation. Okay? And then this side pairing transformation, which is an element of gamma, will also move this Euclidean line to a new Euclidean line. Okay? And then she travels along this Euclidean line this way here, and this part of the circle, and then she reaches another side of this fundamental domain, and then she gets moved to another side by another side pairing transformation, and so on and so on. So this looks much more complicated than the Euclidean case, right? So can you find it out actually in this way, which place in this closed hyperbolic surface does she get to visit? Now, Hedlund says that, nevertheless, any Euclidean line in a closed hyperbolic surface is dense. Okay? You can start from anywhere in the closed hyperbolic surface as long as you travel along the Euclidean line. You get to see everywhere because the line becomes dense. Okay? So traveling along the closed hyperbolic surface, as long as you walk along the Euclidean line, is pretty safe. You get to see all the places. And I want to say this theorem about Hedlund is very specific about Euclidean line because if you travel along hyperbolic line, then it's not guaranteed that you will be seeing all the places in a closed hyperbolic surface. Because the closure of the hyperbolic line can be very wide. It can accumulate in just some part of the closed hyperbolic surface. Okay, so your travel agency cannot guarantee that I will show you all the places if you travel along hyperbolic line. So how does Hedlund prove this theorem about this closure of the Euclidean line? So he goes upstairs. So what do I mean by upstairs? So we have identified H2 with this quotient of PSL2R over SO2 via the isometric action of PSL2R. And this isometric action of PSL2R on H2 can be extended to an action of PSL2R on the unit tangent bundle of H2. Okay? So T1 of H2 is a notation for the unit tangent bundle of H2 this is simply the collection of all the unit tangent vectors, like these arrows. So, and then a PSL2R act over there transitively. And moreover, the stabilizer now becomes trivial because you think about this upward normal vector based at I. Remember, the stabilizer of I was the rotation group, okay? So then now I have a vector. So because if you want to fix this vector, you first have to fix the base point, which means that you have to be a rotation element. But then, of course, you don't want to rotate it if you want to fix this vector. So the stabilizer of a vector here is a trivial, which means that indeed T1 of H2 is just PSL2R period without any quotient. Okay? So this Lie group PSL2R can be identified with the unit tangent bundle of H2. Moreover, so here's the relation of the Euclidean line in this picture. So if you consider this upper triangular group, this is a one parameter upper triangular group, certainly a subgroup PSL2R because the determinant is equal to 1, right? So this is the group, continuous one parameter group consisting of these upper triangular matrices. And because this is subgroup PSL2R, so this group acts on the unit tangent bundle by just multiplications on the right. Okay, you can start from any vector, which means that any element of PSL2R, and then you look at that element times all the elements of U. That's what I mean by the U orbit. Okay? And this U orbit, it traces out Euclidean line. So for instance, if I look at this upward normal vector, which I consider as an element of PSL2R, then this U orbit will be all the upward normal vectors on this horizontal line, on this Euclidean line. Or if I look at this downward vector here, then this U orbit is going to be all the inward normal vectors on this Euclidean line, which is the circle tangent to the boundary. So this is a relation between U orbits and the Euclidean lines. And this picture is preserved when you quotient by gamma. So meaning that, so remember our closed hyperbolic surface is of the form H2 by gamma. And since we have identified H2 with the PSL2R mode SO2, so this quotient can be considered as this double quotient. And then the unit tangent bundle of this surface is actually this space PSL2R mode gamma. Okay? So the point about going from this space to that space is that because here this is a double quotient, I cannot act by my subgroup, but then if I go upstairs, then action makes sense because I can multiply any element of PSL2R from the right. Okay? And moreover, as we just observed, for any Euclidean line, it can be realized as a projection of some U orbit upstairs to downstairs. So here's the picture you can imagine. So she was traveling along Euclidean line, but now the action on XU, you can think, okay, she is traveling with some arrow, and then you can also see how the arrow, where the arrow is pointing when you look at this U action. So because of this correspondence, if we understand what is the closure of U orbit upstairs, then we'll understand what is the closure of a Euclidean line downstairs. And in fact, actually, Hedlund's theorem is proved upstairs. Okay? So meaning that his theorem says that for any vector or for any element in this quotient space PSL2R by a co-compacted discrete subgroup, the closure of this U orbit is everything. So we can interpret actually this theorem in the following way. So we already said that the Euclidean traveler gets to see all the places in closed hyperbolic surface, but this theorem says that not only she sees actually all the places, but she can appreciate these from every angle. Okay? She can also appreciate this every object from every possible angle. So this is much stronger statement. Okay, so now we move to a higher dimension hyperbolic manifold. So for any n, so Hn is again, this is a half space of n-dimensional Euclidean space. Okay? So we have x1 to xn minus 1, and then I denote the last nth coordinate by y, and then the y has to be positive. And then the hyperbolic metric is the Euclidean metric, again, divided by the last coordinate. Okay? So here's the picture. So, okay, so this plane is for the y is equal to 0, and then again, as before, the plane is not contained in the n-dimensional hyperbolic space. It is only the boundary. And in this model, the geodesics are again the vertical lines or the semicircles intersecting the boundary orthogonally. And again, Hn is almost a group in the sense that the isometry of Hn, which this is orthogonal group of signature n, 1. So you might wonder, because I said previously isometry of H2 is PSL2R, and then now I'm saying the isometry of H2 is SO2, 1. But indeed, SO2, 1 is isomorphic to PSL2R. So what I'm saying here is consistent with our previous. And any closed hyperbolic n manifold, then it's a quotient of Hn by a discrete co-compact subgroup, as before. Okay? And gamma is a discrete co-compact subgroup of isometry of Hn, which is SOn, 1. And for closed hyperbolic surface, we said that there are, in fact, uncountably many closed hyperbolic surfaces. But in fact, it is much harder to find actually closed hyperbolic n manifold if n is at least 3. Okay? Because there are only countably many closed hyperbolic n manifold. Okay? But nevertheless, there are infinitely many and also countably many closed hyperbolic n manifolds. So this is a consequence of something called the local rigidity theorem due to Selberg, Calabi, and Bay. Okay? So okay, so still we have infinitely many closed hyperbolic n manifold with for any n, at least 3, so she wants to travel. So what is now Euclidean line? Okay? So in this apart space model, we have this horizontal plane given by the equation y is equal to n, y is equal to 1, right? So this is horizontal plane, and by Euclidean line, we mean actually any line on this horizontal plane. Okay? And again, there are isometric images. Their isometric images will again look like some circle but tangent to the boundary. These will be isometric images, and they are all called Euclidean lines. So again, so we have this quotient map, and then Euclidean line in this quotient closed hyperbolic n manifold is the image of the Euclidean line from Hn under this quotient map. So what are the possible closures of Euclidean line in this closed hyperbolic n manifold? So in fact, Ratner actually answered this question, and I want to describe her theorem, but her theorem is actually much more general beyond this setting of hyperbolic n manifolds. So the setting is this. So let G be any simple Lie group. Okay? So for instance, it can be SLNR, or it can be this orthogonal group of signature n, 1. Okay? And let gamma be a discrete subgroup, any discrete subgroup. Then we can form this quotient space, G mod gamma. And if you have a subgroup U inside the G, then you can just, you have a natural action of U on this quotient space just by translation on the right. Okay? So there's a notion of U orbit for any subgroup U of G. And the question is that you just choose some starting point in G mod gamma and then look at this U orbit. Can you describe the close of U orbit? Okay, so what is the closure of this XU? Okay. So there is this theorem of Moore called the Moore-Salgadis theorem from 1966, which says that if your G mod gamma is a compact space, okay, compact space, or more generally, if this has a finite volume, so there are non-compact spaces with finite volume, and if your subgroup is a non-compact subgroup, then in fact, for almost all x, okay, for almost all random x, the orbit closure will be everything. Okay? So you have G mod gamma, and then for almost all choice of your starting point, you will be able to see everywhere. Okay? But this is not very good for our traveler because she doesn't know where to start. So this statement is about the existence of many dense orbits, but it doesn't say which starting point you get a dense orbit and which starting point you get something else. Okay? So it's not good, and the Ratner theorem fixes exactly this issue. So this theorem was initially conjectured by Raghunathan, and it was proved by 1991 by Ratner, and this is a statement. So suppose we have a finite volume homogeneous space. By homogeneous space, I mean the quotient of simple Lie group by a discrete group. But it is important that it must have a finite volume. And suppose U is any subgroup of G, but generated by unipotent elements. Okay? So what is a unipotent element? So because we are always considering matrix group. So a matrix is a unipotent means that all of its eigenvalues are equal to 1. Okay? For instance, this is a unipotent matrix because the eigenvalues are 1s here, right? So matrix is unipotent if all the eigenvalues are equal to 1. And her theorem says that as long as your group is generated by unipotent elements, then for any x, okay, you give me any x, and then she describes what is the closure of this U orbit. So the closure of XU is always another homogeneous space given by some closed Lie subgroup. Okay? So H is some closed Lie subgroup of G, and if H is everything, then of course you get a dense orbit. But it happens that you can have a closed proper subgroup of G whose orbit becomes closed inside the big G mod gamma. Then of course there is a possibility of U orbit sitting over there. Then you cannot get out of this closed homogeneous space. Okay? But her theorem says that these are all the possibilities. Okay? So going back to our closed hyperbolic manifold, so how do we apply actually her theorem in our setting? So we have this Hn mod gamma, and then we wanted to understand the Euclidean line. So again, we go upstairs because we want to see a space where we can see the action. And then in the manifold, it is hard to get an action. So this time, we go all the way to the frame bundle of the manifold. Okay? So it's a frame bundle, meaning that element in this frame bundle is also normal frames in Hn. Because this frame bundle can be identified with this quotient, SON1 by gamma. Not the double quotient, but the single quotient. And moreover, every Euclidean line is a projection of some U orbit. And this U is this one parameter unipotent subgroup. Okay? It looks complicated, but I wanted to show it to you because, okay, eigenvalues are all equal to 1. So this is a unipotent one parameter subgroup. So again, as before, okay, so to understand the closure of Euclidean line, it suffices to understand the closure of U orbit. And then Ratner's theorem described us that because it was G mod gamma, and then we are assuming this Hn mod gamma is a compact, which means that this space is also a compact space. So her theorem applies. Okay? So her theorem gives the following statement. Start with any closed hyperbolic manifold. So it means the compact hyperbolic manifold without boundary. Then the closure of any Euclidean line is a closed hyperbolic submanifold. Okay? So up to a tilting, which I'm going to describe very soon. So a special case of this theorem when n is equal to 3 says the following. So if you look at the closed hyperbolic 3 manifold, then there are only two possibilities. Because this hyperbolic submanifold cannot be a hyperbolic, one-dimensional hyperbolic geodesic, right? Because it has to contain Euclidean line. So there are only two possibilities. It is either two-dimensional closed hyperbolic submanifold or everything, because our entire space has dimension 3. Okay? So in this case, this theorem says that every Euclidean line is either dense in some closed hyperbolic surface, like in this picture. I might have some closed hyperbolic surface in my ambient space, and then I might have started, she might have started inside from this closed hyperbolic surface. Then, of course, she cannot get out. Okay? But it still, nevertheless, it guarantees that she will be able to see everything in some closed hyperbolic submanifold, or it becomes dense. So you have this dichotomy. Either it is dense, or it is dense in some closed hyperbolic submanifold. Okay? Now, in higher dimension case, so in general, so there's more possibility, and then I have to describe what this tilting is. So by closed hyperbolic submanifold, what we mean is that, so you have this Hn, and then you consider this hyperbolic subspace Hk, okay? And this image of Hk under the quotient map might become closed, might become compact, and then this is how we get closed hyperbolic submanifold. So this is the picture of a codimension 1 hyperbolic subspace, and tilting means that instead of this, so we tilt this vertical hyperbolic subspace in this way. Okay? So you get this slanted subspace, and this is what we call tilted subspace from a hyperbolic manifold. Okay? So when the image of this subspace becomes closed, in fact, the image of this tilted version will also be closed. And then, so this appears in the statement. And that's what we mean by up to tilting. Okay? But we can somehow think of this tilting operation analogous to this translation operation in our statement of the Euclidean torus. So I want to just point out this remarkable analogy with the Kronecker's theorem from 1884. It was that in any Euclidean torus, the closure of a Euclidean line was a Euclidean subtorus up to translation, but we have exactly analog statement in a closed hyperbolic manifold. The closure of Euclidean line is a closed hyperbolic submanifold up to a tilting. So as long as she travels along the Euclidean line in a closed hyperbolic manifold, she will be seeing some hyperbolic world. Okay, so now we want to move to infinite world. So she was happy about traveling all this closed hyperbolic submanifold, and then she wants to now have a new adventure of going to an infinite volume hyperbolic manifold. Okay? So again, infinite volume hyperbolic manifold is again a quotient of Hn by a discrete group, but this time we don't require gamma to be co-compact. Gamma is just some discrete group, so we get actually possibly some infinite volume hyperbolic N manifolds. So will our traveler again be able to see all the places of some hyperbolic subworld? So it turns out the answer is no for a general hyperbolic manifold of infinite volume. So for instance, there are these examples of a hyperbolic 3 manifold, which is topologically simply product of a closed surface times real line. Okay? And then in this case, we can find out actually, we see there are Euclidean lines which have very wide closures. The closures have some fractal dimensions. So you cannot travel to any hyperbolic manifold of infinite volume. You have to be careful which infinite volume hyperbolic manifold you want to travel. And it turns out hyperbolic manifolds with the so-called Fuchsian ends, these are safe to travel. Okay? These are safe to travel, and then, so now I want to explain what are hyperbolic manifolds with the Fuchsian ends. Okay? So let's start with the two-dimensional case. So hyperbolic surface with the Fuchsian ends are constructed in the following way. So I have some closed hyperbolic surface, and every closed hyperbolic surface has infinitely many simple closed geodesic. Okay? So we know what a closed geodesic is, and simple means that there is no intersection. Okay? So take one of simple closed geodesic here, like in this picture, and then you cut the hyperbolic surface along this closed geodesic. Okay? You cut it, and then you get this compact hyperbolic surface, but with a boundary, right? You cut, and then you open it, and then now you have a boundary component. But then this boundary component can be extended so that we obtain a complete hyperbolic surface. So there is actually a canonical way of, you can think, okay, you have this compact hyperbolic surface with the boundary, and then leave it for a while, and then it knows how to grow. And then it will naturally grow to a complete hyperbolic surface, or you can just glue this, there is a hyperbolic cylinder given by this L times the R plus, and then you can glue it and then get a get a complete hyperbolic surface. Okay? Of course, this is the infinite area, clearly, it's the infinite area, but this is complete hyperbolic surface. And then we call this end the Fuchsian end. So for hyperbolic surface with the Fuchsian end, this is theorem of Darboux, 2000. She proved that any Euclidean line in S is either closed or dense. So remember, Hedlund's theorem says that if you have a closed hyperbolic surface, then every Euclidean line is dense, right? But now actually we have another possibility here, closed or dense. Here by closed, I don't mean periodic or compact. I mean just topologically closed. In this case, it will be just isometric immersion of the real line, because remember, our Euclidean line just looks like this line. And then one possibility is this our Euclidean line may lie in this Fuchsian end, may lie in this flare, and then this two end kind of disappears to infinity. So this is topologically closed, right? Because you just go to infinity. So this is the only possibility. So either your Euclidean line disappears in your flare, or it becomes dense everywhere, including the flare. So there are only two possibilities. So we again have the dichotomy. So if the Euclidean traveler travels in this hyperbolic surface with the Fuchsian end, then she might just disappear to infinity, or she gets to see all the places in this surface. Okay, so now I want to describe a higher dimensional version of this. So for n at least 3, so as I mentioned before, there are countably many, infinitely many closed hyperbolic n manifolds. And then not every closed hyperbolic n manifold contains properly immersed codimension 1 geodesic plane, which is like analogous to simple closed geodesic in a hyperbolic surface. But there are infinitely many of them which contains properly immersed codimension 1 geodesic submanifold. Okay? So you have to think this codimension 1 geodesic submanifold really analogous to this simple closed geodesic in higher dimension case, because this is something that you can cut along because it's a codimension 1. Okay? So imagine, so this is the picture for, say, I have a properly embedded codimension 1 geodesic submanifold, and then I remove it, and then I get again the compact hyperbolic manifold, but with a boundary given by this codimension 1 geodesic submanifold. And as before, there is a natural way of making this hyperbolic manifold a complete hyperbolic manifold by gluing this hyperbolic cylinder, or just you let it stay in hyperbolic world for a day or two, then it will naturally grow. Okay? So this is how we obtain hyperbolic n manifold with the Fuchsian end. Okay? And here I gave you a picture with one codimension 1 geodesic submanifold, but you can if you have any finite number of properly embedded codimension 1 geodesic submanifold which are disjoint from each other, then you can do similar process and then get this picture of a hyperbolic manifold with several Fuchsian ends. So here's a theorem proved with McMullen Mohammadi in 2015 for dimension 3. And then the higher dimension case was actually joint work with my student in 2020 for or n bigger than 4. So the statement is this. So suppose we have a hyperbolic manifold with the Fuchsian ends. So this is the infinite volume. And any Euclidean line in M is closed, because this is a possibility because you can disappear in some flare. Or the closure is another hyperbolic submanifold up to tilde. Of course, here, when I say hyperbolic submanifold, they are not necessarily closed, but it is some hyperbolic submanifold with Fuchsian ends, okay, of a smaller dimension type. Right, so I hope actually I explained what this picture meant. So this is the infinite volume, a hyperbolic manifold with the Fuchsian end. She's traveling, so she either disappears or she gets to see some hyperbolic worlds. How much more time do I have? 10 minutes, okay. So this could have been the ending of my lecture, but I have more in case I have 10 minutes. So let me show you a little bit more. So yeah, here's the part I get to say a little bit about the proof. So how do you prove this theorem? Yeah, how do I prove this theorem? So Ratner proved this amazingly beautiful theorem in the finite volume case. So now, how difficult is it going from finite volume or infinite volume? So what is the main difference? Yeah. What's the main difference? So difficulties in doing dynamics in infinite volume case is this. Suppose my entire world is compact, okay? So I have some U orbit, and what we want to do is we want to understand the closure of U orbit, which means that we want to understand where it accumulates, right? Because the closure is the set of all accumulation points. We want to understand where it accumulates, but if this is compact, then any U orbit remains in a compact subset because your entire world is compact. But if this is an infinite non-compact or even infinite volume, imagine this picture, then you can go out to the flare very, very far, okay? And she might come back, but she can also go away very, very, very far. Okay, maybe she's angry with her parents or something, so she goes very far, and then she knows that she has to come back home at some point and then goes again out. But it's a theorem, in fact, actually, in this infinite volume case, almost all U orbit, they do come back many times, but then they come back only the 0% of time to a compact subset. So 100% of time is spent too far away for us to be able to capture where it accumulates. Of course, when you go very, very far, it's very, very hard to understand the accumulation phenomenon. So this is actually the main difficulty, okay? So how do we capture the accumulation phenomenon in the infinite case? So I just want to give you a little bit about the feeling, like what you had to do. So in fact, what you had to do is the dynamics in fractals, okay? Because we cannot now use the Lebesgue measure idea or something, but we have to now move to a fractal space actually to understand this phenomenon, because in the Lebesgue time, we only see the 0% of coming back. So we don't use now the Lebesgue idea, but the fractal idea. So say in the case of, say, hyperbolic 3 manifold, the main ingredient of proof is that we had to understand the following situation. So the boundary of Hn is in general. So for instance, imagine we had this hyperbolic 3 space. What was the boundary? So boundary was the plane, right? And then also the point at infinity, which we can think of either as the extended complex plane or the extended Euclidean plane. In general, the boundary of Hn is this extended n-1 Euclidean space. Okay? And the isometry of Hn can also be identified as the Möbius transformation, the group of Möbius transformations of this boundary. So this is consistent with our picture of PSL2R, because PSL2R is the Möbius transformations in the extended Euclidean line. Okay? So then, so now I think of this background as the extended Euclidean space R2 hat, and then consider I have this round Sierpinski carpet picture. So by round Sierpinski carpet, what I mean is that I have infinitely many disjoint open disks, round open disks here, right? You see I have infinitely many round open disks. I mean, to be honest with you, there are only finitely many round open disks here, but you have to imagine there are infinitely many round open disks here. Okay? And then my gamma is the symmetry group of this round Sierpinski carpet, meaning that gamma as a Möbius transformation, it acts on the extended complex plane, and gamma consists of all the Möbius transformations which preserves this picture. That's what I mean by symmetry group. Okay? Then in my work with McMullen-Mohammadi, what we had to do is this. So draw arbitrary circle here. Okay? You give me a circle. I don't get to choose my circle. You said, okay, I'm interested in this red circle, and tell me about the orbit of this circle under this symmetry group. Okay? So gamma is a countable group, so I have this, and then I have countably many circles, right, here. And then I had to understand, we had to describe what is the closure of this gamma C in the space of all circles. Okay? This is what we had to do. And then in higher dimension case, now we have a higher dimension around the Sierpinski carpet. And it would have been easy if we could understand maybe the orbit of a higher dimensional sphere in this case. But then to understand this trajectory of a one parameter group, we still had to understand the orbit of a circle, which is much smaller dimensional object than compared to the ambient space. This was much harder. And I mentioned actually the traveler going very far, and then come back to a compact space. And then in this picture, what it means is that, for instance, here, so one has to understand the intersection of this circle, the red circle, with the black part. So when this circle passes through this white round disk, so this corresponds to the time she is in the flare. Okay? And then when this red circle is outside of this white round disks, this corresponds to the time she is in the compact set. So this is, now you can kind of understand why I said that the Lebesgue measure of the time she comes to a compact set is 0, because here you have some kind of Cantor set and the Lebesgue measure is 0. Okay? So, but in higher dimension case, okay, so it's also similar. The white part is something she's very far. We cannot say too much about it. But here actually it's not only whether I am in the white part or blue part, but there is also some complicated forest, okay, which is caused by phenomenon that we don't have a close dichotomy, but there are intermediate forests in between. So it was much harder to understand the higher dimension case. Okay, so this is I wanted to finish this lecture by describing one open problem. So, so this is the problem about Apollonian gasket. So this gives us a special type of hyperbolic manifold, which looks very similar to this hyperbolic manifolds with the Fuchsian end, but there's a difference. So here now you see actually, this is the picture of Apollonian gasket. So you see the point is that when I said the round Sierpinski carpet, the circles were not allowed to touch each other. The circles were all disjoint from each other, but in this Apollonian gasket picture, you have this tangent point here. Okay? So what is now issue? Because now if I consider this circle, then when I'm very, very close to this tangent point, it's not clear whether I am in a compact part or non-compact part. So because of this tangent point, actually, this issue of understanding somehow recurrence to compact part, this is much, much trickier. And then, so this causes actually different level of problem. So it's an open problem, and we don't understand. In this Apollonian cascade, you draw a circle, and then can you describe the close of this circle? We don't know. Okay? So in terms of the hyperbolic three-manifold, it corresponds to this picture. So previously, the Fuchsian end kind of looked like some closed hyperbolic surface times R plus, just this end. But this tangent point actually causes us some kind of cusp from this hyperbolic surface, and then the behavior of this line when it passes near the cusp gets so complicated. But I think this is somehow very beautiful and very natural problem, and then hopefully maybe some of you are interested in this and then solve this. Thank you.